Hey guys, welcome back to another edition of Geometry. It's Mr. Anderson here with you, and that tells us it's time for section 6.6. We're going to talk about trapezoids and kites today, and so let's get started. Our objectives today, first of all, we're going to apply properties of trapezoids and apply properties of kites. Who knew? All right, so let's start out here with trapezoids. The properties of a trapezoid. First of all, very, very important. Again, important because if I can find where my pen is here, I will point out that there are the three asterisks here. A trapezoid is not a parallelogram. We've been talking about parallelograms for a long time. A rectangle, a square, a rhombus, they're all parallelograms, okay? And so this is not, okay? So all the things that we talked about dealing with parallelograms do not necessarily apply to trapezoids. Only what we're going to talk about today applies to trapezoids, okay? All right, so first of all, a trapezoid is a quadrilateral with exactly one pair of parallel sides. Remember, a parallelogram, both pairs of opposite sides are parallel. Here, it's just one pair. So here's what it would look like, something like this. And in this situation here, okay, if this will let me draw arrows here, there's your parallel sides. And notice then these two sides pretty obviously do not look parallel. So there's just one pair of parallel sides. So that's what's going on in a trapezoid. The parallel sides are called bases. So this is a base, and this is a base. Remember back when we were talking about triangles, you know, 1/2 base times height, we had one base. Well, now in a trapezoid, there are two bases, and the two bases are the two parallel sides. The non-parallel sides are called legs. So over here, this would be a leg, and this would be a leg. So the non-parallel sides are called legs. And finally, I'll say this, we'll talk about this more in a second here in the next slide or two. There are two pairs of base angles. I'll say it like that. So for example, if this, let's call this A, B, C, D. So in this trapezoid ABCD, what that means is the base angle is where a base and a leg come together. Well, you go, well, that's everything. Okay, yeah. And so that's why I tried to clarify this talking about two pairs of base angles. So what that means is that A and D kind of go together here. And it'll make more sense in a second. But A and D basically go together as one pair of base angles, and then B and C go together as another pair of base angles. And we'll talk about that right now. Isosceles trapezoids. Okay, so in an isosceles trapezoid, very important here, three asterisks, the legs are congruent. Remember, in an isosceles triangle, there were two sides of the triangle that were congruent. Well, in an isosceles trapezoid, the legs are congruent. Remember, the legs are the non-parallel sides. So it might look something like this. And so let's say we have here A, B, C, D. Okay, so A, B, C, D. In this case, again, this side AB is parallel to side CD. And since the legs are congruent, then that means this side is congruent to that side. Okay, so that's what makes it isosceles, is these two sides are congruent to each other. And so here's where the base angles thing comes into play when we're talking about isosceles trapezoids. What that means is that if we have these two pairs of base angles, in this case, C and D, I think I labeled these a little differently than before, but C and D, that pair of base angles in an isosceles trapezoid, those are congruent. And then the other set of base angles, A and B, are congruent. Okay, so that's why the isosceles trapezoid is kind of cool there, because you have these two pairs are congruent and those two pairs are congruent. Those two angles which make a pair are congruent, and that pair, those two are congruent. And so a trapezoid has one pair of congruent base angles, then it's isosceles. This is kind of an extra thing that they throw in there. That's basically what we just said, is if you have something that's a trapezoid and you knew that C and D were congruent, well then A and B would have to be congruent as well. So it's really just another way of looking at what we just talked about. But the other thing that's very important is the diagonals are congruent. Okay, so again, remember, the diagonals would be, that's not really straight, but why did I make that trapezoid so big? That the diagonals are congruent. So in this case, the diagonal AC is congruent to DB. So the diagonals AC is congruent to DB. Okay, so that's another thing with an isosceles trapezoid that's very important and that you can use perhaps when you're solving things. All right, let's take a look at an example here then. All right, so each side of this basket is an isosceles trapezoid. Okay, so this is an isosceles trapezoid, so the things that we just talked about are true here. So measure of angle JML. So JML is this whole entire thing right here. That whole thing is 130 degrees. KN is 6.7 and LN is 3.6. We want to find MJK. Well, where is MJK? MJK. Okay, so MJK is this angle up here, that whole thing. Any ideas? What do you think? There's probably a couple of ways that you could look at this. One thing that you could do is you could say, well, this is a quadrilateral. There are four sides. So if you remember from before, there are 360 degrees in this quadrilateral. This is angle M here. The whole entire angle M is, or in other words, JML is 130. Then MLK is also 130. Because we know this is one of the pairs of base angles. So they're the same. So if we took 360 minus 130 and minus 130, we just subtracted those two things out, then we would have left 100. Well, 100 degrees is split between J and K. Well, remember, this is another pair of base angles that have to be the same as well. And so that if we take the 100, all we have to do is just divide by 2 and we get 50. J and K are both 50. And so in this case, more specifically, the measure of angle MJK. Okay? The other way that you could approach this, keep this in mind. Haven't talked about this much, but remember, here's your parallel sides here. Remember, in parallelograms, any pair of consecutive angles were supplementary. They added up to 180. Well, this isn't true in a trapezoid for every pair of consecutive angles, but it is true for the two angles that are on the same side in between the parallel lines. So, for example, down here, JML is 130. That angle there and angle MJK would have together to add up to be 180. So we could have made this even a little simpler and just said, hey, if those have to add up to 180, I could just take 180 and then take out the 130, take this out, and what's left is 50. And you notice that's the same thing we got up there. So you can do that with, say, angle J and M. You could do that, and you could do it with K and L. but you could not do it with M and L or J and K. Those won't work that way. And as a matter of fact, those two, J and K and M and L, would be congruent. So you wouldn't be able to do this here. But with the ones that are not congruent, they will add up to be 180. Okay, so a little bonus there. All right, another example here. So we have some of the same things. This time we're going to find MN. So this is what we're trying to find right now. So since I looked at what we're looking at first, we can save ourselves some time by not worrying about JML anymore. That's degrees. And we're talking about the side. So who cares? What we do care about is KN is 6.7. And we know that JL, which is this whole entire thing here, I'll try to do this as best I can. That whole thing is 10.3. Okay, so how do we find MN? Well, MN is this little part here. Remember, in an isosceles trapezoid, the two diagonals are congruent. So that means if JL is 10.3, then MK has to be 10.3. And then to find MN, all we have to do is take that total of 10.3 and subtract out the 6.7. So all we have to do is 10.3 minus 6.7. And then what's left there will give us MN. Okay? And so that would give me 3.6 is MN. All right. Coordinate geometry. Oh, okay, your favorite. All right, what we're going to try to do here in this coordinate geometry is we know we have a quadrilateral. It's graphed for us over here already. We have vertex 5, 1 is A, negative 3, negative 1 is B, negative 2, 3 is C, and 2, 4 is D. We have to show that it's a trapezoid, number one, and then if it is it isosceles? Okay. So what's the thing that makes a trapezoid? Well, it has one pair of parallel sides. Only one pair of opposite sides. If both pairs are opposite, then it's a parallelogram. So what could we do to see if something's parallel? I don't know. Could we do slope? Yeah, remember if we do the slope, if we have the same slope, those lines are parallel. So what we're going to do is we're going to compare, let's start out by comparing the slope of CD and BA. Those look like they're parallel, so we expect those to come out the same. And so we're going to try it. Remember again our slope formula, y2 minus y1 over x2 minus x1. That's our slope formula. All right, let's plug it in. So the slope of, first of all, CD. So I'm going to go 4 minus 3 over 2 plus 2. So that's 1/4. Okay, so the slope of CD is 1/4. And then the slope of, now we want to do BA. So that's going to be 1 minus a negative, so 1 plus 1. And then 5 plus 3. So that's 2/8, which simplifies to 1/4. So guess what? They're the same. So that means that those lines are parallel. So put the arrows in here. So those two lines are parallel. Yay! But remember, just because we prove that those are parallel doesn't mean this is a trapezoid. We have to prove that the other two sides are not parallel. Okay, so we just have to do our parallel lines then on the other ones as well. So let's do the slope of CB first. So on that one, I'm going to go -1 minus 3, and then -3 plus 2. So this would be a -4 over a -1, which is 4. All right, and then let's do the slope of DA. And so in this case, I'm going to go 1 minus 4 over 5 minus 2. So that's a negative 3 over 3, which it looks like is a negative 1. Are those slopes the same? Nope. Nope, they are not the same. So now what we've proved here is we proved that these two sides are parallel, these two are not. So we have now proved that we have a trapezoid. Okay, yay. But there's a second part to the question. Is it isosceles? Okay, well, what does isosceles trapezoid mean? Well, there's actually two ways you could approach it, but unfortunately, both ways involve the distance formula. And so isosceles trapezoid means the two legs would have to be congruent, or if you wanted to, you could do the diagonals are also congruent. So you could do those too. Either way, it's about the same. All right, so fortunately, I planned ahead and made another blank one here so we could work that out on another page. So remember, on this one, we're going to do the distance formula. So this is square root of x2 minus x1 squared plus y2 minus y1 squared. So we're going to use that formula and find the, first of all, find the distance of CB. So we're going to find CB here. So that's going to be, what, x2 minus x1. So I'm going to go negative 3 plus 2. Whoops. Just disregard that. Negative 3 plus 2 squared. And then negative 1 minus 3 squared. So this is negative 3 plus 2 is negative 1 squared is 1. That's a negative 4 squared, which is 16. So for a total of square root of 17. Okay, that's our distance there. We'll see how that matches up with dA. All right, so in dA, I'm going to take the square root of 5 minus 2 squared, and then 1 minus 4 squared. And so 5 minus 2 is 3. 3 squared is 9. And 1 minus 4 is negative 3 squared is 9 again. And so it looks like we have 9 plus 9, which is the square root of 18. Those are different. They're very close, but those are different. And so what we would have to say here is this is not isosceles. Okay, got a feel for that? All right, good. Moving on. The trapezoid mid-segment theorem. So here's a trapezoid, just a regular one. It doesn't have to be isosceles now. Any trapezoid this will work on. The mid-segment connects the midpoint of the legs. And so if we call this, I'm going to call this A, B, C, D, and then I'm going to take the midpoint, say, of AD, and the midpoint of BC, and I'm going to call this E and F. So the mid-segment will just connect those midpoints. So here's more or less, that's the mid-segment. Okay, so EF is the mid-segment. And so here's some things that happen with the mid-segment. First of all, it's parallel to the bases. Remember in this trapezoid, remember these sides are the parallel sides. Well, the mid-segment is also going to be parallel to those opposite two sides, number one. Number two, I don't think I have this listed over here, but since the mid-segment connects these two midpoints, that means that AE will be congruent to ED. And it means that BF will be congruent to FC. They're not all four the same necessarily, but BF and FC will be congruent, and A, E, and ED will be congruent. And then finally, this is going to make more sense when I do an example here, but this, to find the distance of EF, basically you're just taking an average. You just add AB, whatever number that is, plus whatever CD is, and divide by 2, or take half of it, and that will tell you what EF is. It's really just kind of like an average. So let's look at an example here. So here's an actual problem. We're trying to find XY. It's the mid-segment, and we want to find out what that is. Okay, so remember what we're doing is we're just kind of taking an average of these. So it's really, we're saying XY will equal 12, which is this one, plus 40 divided by 2. So 12 plus 40, which is 52 divided by 2, so 26. So this distance here is 26. Okay, pretty easy, right? Now, one thing I'm going to point out before we do the next example here is we followed this little formula, add them together, divide by 2. Sometimes you're not given those two numbers. You might be given one side and the mid-segment, and you have to find the other side. I'll show you how you can still use that same formula, but take a look at this. To get from this side 12 to 26, what's the difference there? It's 14, right? 14 units away. If you go another 14 units from 26, what do you get to? 40. So if it's 14 from here to here, it'll be 14 from there, 26 to 40. So that might be another way you can approach the next example here as well, because look, we have 20 and 30. So using what I just talked to you about before with some logic there, you go, well, if 20 is 10 units away from 30, what should this be here? It should be another 10, which would make this 40, right? Well, let me just show you kind of how that works. Remember the formula would be, if you think of this as x, you're just going to say, well, x plus 20, so the outside ones, add them together, divide by 2 would have to equal the mid-segment, 30. And then if you solve that, you go times 2. X plus 20 equals 60, minus 20. X is 40. So if you do the mathy way, it still gives you the same thing. It might be easier to just use some common sense and some logic there when solving a problem like that. Okay, last thing we have to talk about is kites. So I'll try to be quick on this, but first of all, a kite is not a parallelogram. Just like a trapezoid, it is not a parallelogram. So only what we talk about here is true for kites, not all those other things with parallelograms. All right, what is a kite? A kite is a quadrilateral with exactly 2 pairs of consecutive congruent sides. So it looks something like this. And so you notice it's a quadrilateral, 4 sides, and the consecutive sides are congruent. So AB is congruent to BC, and AD is congruent to DC. That's a kite. All right, so here's a couple of things about kites that can happen here. First of all, you notice that these 2 sides and these 2 sides are congruent. Also, the diagonals are perpendicular, so they make a 90-degree angle in here. That's something else that we can use. And then the other thing is exactly 1 pair of opposite angles is congruent. And so if you notice here, it's angle J and angle L. So it's the 2 angles that are in between the sides that are different lengths. So this has 1 mark and 2 marks, and then this has 1 and 2. It's the angles that are in between that. So, so for example, on this one right above it, the angles that would be the same would be ABC, angle ABC over here, and then ADC, that angle. Those would be the angles that are congruent on that kite. Okay, so a couple quick examples, and we will be done. It's a kite, find x, y, z. So we want to find x, y, z. We want to find this one down here is what we're trying to find. Remember, in a kite, we were just talking about this, these 2 angles are the same. So this would also be 121 degrees there. And so we know since a kite has 4 sides, it has 360 degrees. And so if we take away the 73, and we take away the 121 and another 121, we just 360, take all those away. and it looks like you'll get 45. So we know that XYZ down here has to be 45 degrees in order to make that all work. Not too bad, right? All right, last one. It's a kite. Again, we want to find NP. That's this side right here, NP. Another thing we know about kites, remember, is that the diagonals make a 90-degree angle. And so, if that's 90 degrees, well, if you notice, here's kind of how we have to do this. We have to kind of stitch something together here. We know if this is 90 degrees, we can do the Pythagorean theorem to find MN, and since MN is the same length as NP, then we can know what NP is. So we'll do the Pythagorean theorem. Remember, that's a squared plus b squared equals c squared. 6 and 8 are your a and b. Remember, a and b are the two sides that make the 90-degree angle. So this is going to be 6 squared plus 8 squared. So 36 plus 64. These together will give you 100. And how we get rid of the square is square root. And in this case, it happens to work out really nicely. So c would equal 10 when we take the square root. So this is 10, and it's the same as NP, so that is also 10. NP equals 10. All right, that's it. This was a little bit longer than some of the other ones. I'm sorry about that. I was kind of going through as best I could, but appreciate you being here. That's the end of Chapter 6, and so next time I see you, we'll be in Chapter 7. We'll see you there. Bye.